So, good morning. Welcome to Krishna's classroom. We continue from where we left last time, and in this talk, we explore the structure of Lebesgue measurable sets M. So, M is defined, that is script M. We denote the set of all E, a subset of R, with the property that E is M star measurable. Now this means, M star is the outer measure. It is defined for every subset of R, but we isolate from it the following class of subsets, namely, that is, see, E is M star measurable. Or what you call Lebesgue measurable. If M star of A equal to M star of A intersection E plus M star of A intersection E. Now this we have explored. This is true for every A belonging to the power set of, that means for every subset A of R. So you know that for every subset M star is different. And what it says is that A is cut rather properly, in the sense that A is actually cut into two pieces, A intersection E and A intersection E complement. And their intersection of these two portions is empty, and the union of these two portions will give you the whole space. So E performs a cutting of A, and what you demand is that the M star of A should be equal to M star of the two portions to which E cuts it. Okay, what's the meaning of that? So it's actually pictorially this is I'm using a Venn diagram. This is A, this is E, and you have this is A intersection E, and this portion is A intersection E. So you want A to be cut into two pieces, A intersection E and A intersection E complement, and we should have M star of A intersection E plus M star of A intersection E complement to be equal to M star of such sets. E is what you call the measurable class, and we have already proved that M is a non-empty class R belongs to M, empty set belongs to M, then M is closed under finite union and intersection. Okay. So this we call, hence, structurally A is M and algebra. We have earlier used the script A to designate this algebra, but let us denote it by script M. That's why I defined it in the itself. Now we go further. What we want to show is that it is closed under countable union and therefore countable intersection. This is what we want. So that M is what is called a sigma algebra. And this is the desirable structure that we need to do analysis on. Okay. So what is to be proved is that M is closed under countable union, and from that you can deduce that it is also closed under countable intersection. Now let us do that. Okay. Now before we prove this result, what we observe is this. Observe that the union of a countable collection of subsets of R is also the union of a countable collection of pairwise disjoint Now, this is a general result. There's nothing to do with R. So, let us give a brief. Let countable collection of by which you mean this M star measurable. Subsets. Now define A1 prime, A1, and for k greater than or equal to AK prime equal to AK slash I equal to 1 to k minus 1 AI. That is what you make this as A1 same as A1 prime. Now you take A2. So this is A2. And what you do is you remove from A2 A2 prime. So this is your is A2 and so on. So you work. Okay. Now since the collection since the collection of measurable sets each AI and M is an algebra, it's an algebra. We have A1 equal A1 intersection A2 complement, A1 intersection A2 complement, A1 slash A2 is this one. So it is A1 intersection A2 complement, and this is equal to A1 complement union A2 complement. Okay. And therefore, you see that this is measurable, because if A1 belongs to M star, A1 star belongs to A1 complement belongs to M star, A2 belongs to M star, and it is closed under, script M is closed under finite union. Therefore, these two, the union becomes an element of M star and its complement is M star. So, we have this property, right? Now, what you have is this AK prime equal to AK slash union I equal to 1 to K minus 1 AR. And that's equal to AK intersection complement. And then of course you use this property. Okay. Therefore, one can conclude that okay, we can argue that AK prime is M star measurable. And now AK prime is a collection of measurable sets whose union is A. So we have each AK prime M star measurable, and we have this and we have the following property, that union of AK prime is equal to now each AK prime is disjoint, therefore union AK is Now union AK is AK prime is a disjoint union of measurable sets. Hence, union K equal to 1 to infinity, AK is equal to union K equal to 1 to infinity, AK prime is a union of countable union of disjoint so thus we have shown that if you have a countable union of measurable sets, it can be written as a countable union of disjoint measurable sets. That's the part. Therefore, what we have to now prove is the following. Is this now given a countable union of or a countable collection of measurable sets is their union, their countable measurable. This is the question that we are taking. So that the collection of all measurable sets will become a sigma algebra. Okay, let us now start proving this thing. So let us state the theorem. The union of a countable union of collection of M star measurable sets is measurable. M star measurable. That's what we want. Okay. So you see that if you, what we have proved earlier is this property is valid under finite union. Okay, but now we are going to go further and say that under countable union also the same property holds. So we'll give a proof. Yeah. So let E be the union of a countable collection of M star measurements. Then there exists a countable collection of M star measurable sets a disjoint. This is what we have said earlier. There is a disjoint countable collection of M star measurable sets EK such that E is equal to okay, where EI intersection J is empty whenever I is not equal. So what we want to assert is that E is measurable. We have seen that if E is the union of a countable collection of M star measurable sets, you can rewrite this as the union of a disjoint disjoint countable collection of M star measurable sets by the remarks that we have made earlier. Okay. So we now prove that E is measurable. So what we prove is that therefore what you need to show is the following. It is sufficient to show that M star of A is greater than or equal to M star of or if we show this inequality, the other inequality is an obvious one. M star of A is less than or equal to M star of A intersection E plus m star of A intersection E complement. That comes from the subadditivity. And if we can prove this, then for every A, the power set is a member of the power set collection of R. Then we are done. Okay, so we try to prove this. Okay, so what we do is, see, make the following observation. Define it's a finite union of EIs. Okay. Now, from what we have proved earlier, is Fn is m star. Because it is the finite union of measurable sets. Further, what we have is that Fn complement is E complement, or E complement is contained in Fn complement. That's simple. Because you see that Fn is so let us now work out this m star of A, m star of A intersection Fn plus A intersection Fn complement. That is because Fn is measurable, and this is greater than or equal to, we are going to make use of this property, m star of A intersection Fn plus E complement, because we use this inequality. Okay, that is E complement is contained in Fn complement. Therefore, this is greater than that. And now we also know that m star of A intersection Fn, this is equal to m star of A intersection EK, and this, you know, is equal to sigma m star of A intersection EK. K running from this we have proved already. Okay. Therefore, making use of this property, m star of A is greater than or equal to sigma A equal to 1 to n m star of plus m star of okay. So this inequality we have, or in other words, for the sum, for this particular sum, m star of a acts as a bound. Okay. Now we use this fact, it is the fact that the left hand side is independent of n, and therefore this should be valid for every, that's our okay. Since the left hand side it follows that m star of a is greater than or equal to now we use the countable subadditivity. By the countable subadditivity, it follows that we have m star of which is less than or equal to sigma infinity now use this result here. Okay, so therefore this inequality. It now follows that all that you need is use this inequality over here. Okay, follows that follows that m star of a is greater than or equal to m star of Okay. Therefore, E is, that is, countable union of measurable sets Now, a consequence of this, we can write that okay, therefore, that is now one of the consequences of this is this, that is under countable intersection. That is because if E is measurable, E complement is measurable. Make use of that. Okay, right? Therefore, what is that you infer? So we conclude script M is a sigma algebra. What does it mean? Means that is one R belongs to A, the empty set belongs to A, two E belongs to implies E complement belongs to A, EK for K belonging to not A, I am using script M. For K equal to 1, okay, then countable union of, this statement that I have made does not require EK, EI, the collection EK to be mutually disjoint. That is not okay. So the consequence of the corollary is that also closed under countable intersection. So now all those finite things can be replaced by countable. So therefore script m is a sigma. That's what we have said. Okay. So that is the structure of this class. Now what we have to do is the following. There are two more things that we want to do. What we want to do is that every interval belongs to the script m, the set m. Okay. So we continue now. Show that every interval an element of script m. And the consequence of this is that, as we shall explain later, all open sets of R are in script m. Therefore, all closed sets are in script m. Okay. Now, not only that, see, open sets are closed under arbitrary unions. What we can say is that all countable union of open sets are measurable. Okay, right? No, that's an open set. That's clear. Not only that, the countable intersection of open sets is measurable. Okay, whereas you see countable intersection of open sets may not belong to the topology. You cannot say that it's an open set. Okay, right? And therefore the so-called F sigma and G delta sets are all in this class. So what we want to eventually conclude is that script m is a huge class of subsets of R, which is measurable. Okay. Although it doesn't, eventually we shall see that it doesn't take care of every element of VR. Okay. That means there are some subsets of R which are not possibly. Okay, I think with these remarks, let me stop here and continue with it next time. And next time our agenda is to prove that all intervals are measurable. And also we want to show that the translate of any measurable set is measurable. Okay, and we have already seen that for intervals, the m star of an interval is its length. So later we shall put all these informations together and define what is called the Lebesgue function. So, okay, thank you very much.